Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to discuss on the topic BJT DC load line analysis. Please note, in one of my previous videos, I have discussed about the common emitter configuration of the BJT. That video will be a prerequisite for the discussion of the topic in this video. So, I highly recommend you to watch that video first before continuing with this video. You can watch it by clicking on the link shown in the top right corner right now, or I will leave the link of the same in the video description below. Coming back to this video, let us start by first understanding what is a load line. In graphical analysis of nonlinear electronic circuits, such as the ones including either a diode or a transistor, a load line is a straight line drawn on the characteristic curve, which is a graph of the current versus the voltage. The next question that we should ask is, what does a load line represent? Well, the load line represents the response of the linear part of the circuit connected to the non-linear device in the circuit. Please note, when I say linear part of the circuit, I am referring to the circuit elements such as a voltage source and a resistor. And when I say non-linear device, it is either the diode or the transistor that is being used in the circuit. So, in simple words, we can say that a load line represents the constraint put on the voltage and current in the non-linear device by the external circuit. Another important thing to note when we are discussing on the load line is the operating points or the Q points. Let us understand what are these points. The points where the characteristic curve that represents the nonlinear device and the load line that represents the linear part of the circuit intersect are the possible operating points or Q points of the circuit. It is at these points the current and voltage parameters of both the linear and nonlinear parts of the circuit will match. Let us start discussing the BJT DC load line analysis by considering an NPN transistor in common emitter configuration and particularly biased in the active region of operation as in figure 1 here. Let the supply voltage VCC be equal to 10 volt. This value of VCC will now forward bias the base to emitter junction and at the same time reverse bias the collector to base junction. Since the base to emitter junction is forward biased and the collector to base junction is reverse biased, the transistor now operates in the active region of operation. The output characteristic curves for the considered circuit is shown in figure 2 here. Please note, this is a common emitter configuration and therefore the output characteristic curves appear in the first quadrant. The x-axis is the voltage across the output terminals, which are collector and emitter, and y-axis is the output current, which is the collector current. Here we have shown the variation of the output current, which is the collector current, for different values of the base current IB, which is the input current. Let us now draw the DC load line on this output characteristic curve. To draw the load line, let us apply KVL to the base to emitter loop and then to collector emitter loop and find the expressions for IB and IC respectively. To start with, let me apply KVL to base to emitter loop. When I apply KVL to the base to emitter loop, the resulting equation would be VCC minus of VBE minus of IBRB equal to 0, where VBE is the voltage across the base to emitter junction. If I now rearrange this equation for the base current IB, the equation would be VCC minus of VBE divided by RB. These equations are shown here and let these equations be called equation 1 and 2 respectively. Coming back to the circuit, let us now apply KVL to the collector emitter loop and the resulting equation would be VCC minus of VCE minus ICRC equal to 0. If I now rearrange the equation for IC, it would be VCC minus of VCE divided by RC. Another very important equation for the common emitter configuration is the relation between the output current and the input current, which is given by IC equal to beta IB. These equations are written here as equations 3, 4 and 5 respectively. Having now found the equations for the input and output currents, let us now learn how to draw the DC load line. To plot the DC load line, we need to find a point on the x-axis by applying IC equal to 0 in equation 3. Let me write equation 3 for your reference here. It is VCC minus of VCE minus ICRC equal to 0. So, we need to now substitute IC equal to 0 into this equation and find the value of VCE. In a very similar fashion, we also need to find a point on the y-axis by applying VCE equal to 0 in equation 4. Let me write equation 4 here. It is for collector current IC and it is equal to VCC minus VCE divided by RC. So, we need to now find the value of IC by applying VCE equal to 0. I will start by first finding the point on the x-axis. So, as already said, substitute IC equal to 0 amperes into equation 3. This is equation 3, please note. So, I am substituting IC as 0 and simplifying the equation, we will obtain VCC equal to VCE. Please note, the x-axis of the output characteristic curve is VCE. Therefore, the point on the x-axis where the load line meets is given by VCE equal to VCC at IC equal to 0. Let us now find the y-axis point. So, substitute VCE equal to 0 into equation 4. Please note this is equation 4 and simplifying that you will obtain IC as VCC divided by RC. Therefore, the point on the y-axis where the load line meets is IC equal to VCC divided by RC and this is obtained for VCE equal to 0. Coming to the characteristic curve once again, please note we have now found 2 points, one on the x-axis which is equal to VCC and another on the y-axis which is equal to VCC divided by RC. These are the points where the load line meets the axis. So, if I now simply join these 2 points by a straight line as what is shown in the dark colored line here, then that line represents the load line. You should note that the characteristic curves as shown in the blue colored curves here represent the nonlinear device which is the transistor and the load line which is shown by a dark colored black straight line, this represents the linear part of the circuit. It should be noted that the location of the load line depends upon the values of the voltage source VCC, resistance across the collector RC and the base current IB. If these values are changed, the load line will also change. I will discuss about that at the last part of this video. Let us now discuss on finding the Q point. Please note, we now have a load line which represents the network and the characteristic curves which represent the device. The point of intersection of these 2 curves is called as the operating point or the Q point. To find the exact location of the Q point, we have to simply draw a line from the Q point to the x-axis, just like this. By doing so, we obtain the x coordinate of the operating point and let me denote it as VTQ. It should be noted that VTQ falls on the x-axis and therefore, this represents the transistor's voltage. In a similar way, if we now draw a line from the Q point to the y-axis like this, then we obtain the y coordinate of the Q point which is, let us say, ITQ. Since ITQ falls on the y-axis, this value represents the transistor's current. So, we can now say the location of the Q point is VTQ, ITQ. Let us now understand what information does the Q point give about the transistor that is used in the circuit. Well, from the Q point we learned that for the applied voltage of VCC, load resistance of RC and a base current of IB, the voltage and current across the transistor are VTQ and ITQ respectively. Well, that is about drawing the load line on the characteristic curves of a device. Let us now understand the impact of variation of different circuit parameters on the location of the load line as well as the Q point. For example, let us consider the scenario where the value of the input current IB is changed by varying the value of the base resistance RB. As you can see, we have characteristic curves for different values of the base current here. Therefore, for this scenario, the Q point moves up or down the load line as shown in the figure here. Please note, this movement of Q point is for variation of the input current IB. I would like to remind you once again that this graph is for variation in IB while the value of VCC and RC are fixed. Let us now consider the second scenario where the supply voltage VCC is held constant and the resistance at the collector RC is varied. For this condition, we have two different scenarios to analyze. The first one is when the value of input current is fixed and the second case is when the value of input current is varied. Since value of VCC is held constant, if I change the value of RC for a fixed value of the input current IB, then the Q point will move towards the left as shown in this arrow here. On the other hand, if I consider the same scenario for a variable value of IB, then the Q point will move in this fashion, that is, it is being shifted down. This is the variation of Q point and the location of the load line when VCC is held constant and the resistance at the collector is varied. Please note, we have analyzed this scenario for both fixed value of the input current IB as well as the variable value for input current IB. Lastly, let us consider the third scenario where the resistance at the collector RC is fixed and the supply voltage VCC is varied. Let us assume that I am going to decrease the value of VCC. So, the location of the load line on the y-axis keeps on changing and it drops down in its value. At the same time, if I assume the value of input current is fixed, then the Q point will shift left as what is shown in this arrow direction. On the other hand, if I assume value of IB being varied, then the location of the Q point will shift down like what is being highlighted here. This is how the value of VCC impacts the location of the load line as well as the Q point. Well, with that, we have now come to the end of this video on BJT DC load line analysis. In my next video, I'll discuss upon the single stage RC coupled amplifier circuit. So, stay tuned. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.